Hello class. Today we're going to review section 5.3b, exponential equations. Now objectives for this, we're going to solve an exponential equation by writing it in logarithmic form, and we're going to convert logarithms using the change of base formula. Now in order to solve exponential equations using the logarithmic form, what we first need to do is to rewrite the equation with the term containing the exponent by itself on one side. Then we're going to divide both sides by the coefficient of the term containing the exponent, and we're going to change the new equation to logarithmic form. Then we're going to solve for the variable. So let's try an example. It says let's solve the equation 3000 equals 150 times t, or times 10 raised to the 4t. For t, by converting it to logarithmic form and graphically to confirm the solution. So first thing we're going to do is divide both sides by 150. Okay, so if our original equation is 3000 equals 150 times 10 raised to the 4t, first thing we're doing, dividing both sides by 150. If we do that, we get 20 equals 10 raised to the 4t. At this point, what we're going to want to do is rewrite it in logarithmic form. Okay, so it's going to be log. Technically, I like to write this on my first step. I like to write 4t equals the log base 10 of 20. Okay. Obviously, the log base 10 is the same thing as just the basic log log function here. So you can write it as just log 20. But keep in mind, if your base is anything other than 10, you can't just write log. You have to write the base with it. But here we do have the special case where it's 10. So we just jump down to log of 20. Now, we're going to divide by 4 on both sides. That'll be our final step there to solve for t. And if we divide by 4, we get t equals the log of 20 over 4. Which you can use your calculator to approximate at 0.32526. Now, if you want to graphically check yourself or graphically solve here, essentially what you're going to let happen is you're going to let 3000 be one of your y's, and you're going to let 150 times 10 raised to the 4t be the other y. And then you're going to run that intersect function. If you run that intersect function right there, you will be able to find that intersection value. Remember, you get to the intersection function by hitting second trace or second calc, and then you go down the intersection. It takes 3 enters in order to find that intersection. First enter isolates the first curve, second enter isolates the second curve, third enter needs to be near the guess point of where you think they intersect, and it will find it for you. Now, let's look at this example about doubling time. We want to prove that the time it takes for an investment to double its value is t equals the natural log of 2 over r, if the interest rate r is compounded continuously. If we start with the compounded continuously formula, which is s equals p times e raised to the rt, what we're going to want to do is we're going to want to substitute 2p in for s. And the reason that we're going to want to do that is because we want to double our initial value. Keep in mind here that p is our initial value, and that s here is our future value. Okay, if we want to double our future value from what our initial value is, that would be a 2p. So that's the reason we substitute 2p in for s here, because we want a doubling of that initial value p, and that's what we want the s to be. Now when we do that, we're able to divide by p on both sides, and these p's cancel out. This leaves us with 2 equals e to the rt. Okay, now we're going to convert this exponential form to a logarithmic form. Keep in mind here that this is log base e equals 2, or log base e of 2 equals rt. That is the conversion of this into a logarithmic form here. Okay. Also, we know that the log base e can be more naturally written as the natural log. Okay, so this is all we've done in this next step is we've changed the log based e to a natural log here. So we have the natural log of 2 equals rt. Now we're essentially trying to solve for t here, so we need to divide by r. And when we divide by r, we have our final formula here, and we have proven that the time it takes to double when compounded continuously is t equals the natural log of 2 over r. Now, we're going to take that fact and we're going to use it in part B. Because suppose that $2,500 is invested in an account earning 6% annual interest, compounded continuously. How long will it take for the amount to grow to $5,000? Well, if we're starting out with an initial value of $2,500 and we want it to grow to $5,000, essentially this is a doubling from our initial value to our future value. Okay, so we can use our doubling formula here. T equals the natural log of 2 over r. What is r? R is just our interest, right? Our interest rate. Here, that's 6%. So all we're doing is saying, okay, t equals the natural log of 2 over 0.06. You do have to write it as a decimal because we need to convert from a decimal to a percent in order to actually calculate here. So t equals the natural log of 2 over 0.06, which gives us approximately 11.5525. So a little over 11 and a half years there. Okay. You could also find this by graphing if you wanted to, but it's easy enough just to plug in the formula. Something to keep in mind, if you don't have a newer style calculator or you have a really old calculator, most of the calculators I've seen this year have the actual log base formula in it that we have used in several of the previous lectures and that I hope that you continue to use. However, if your calculator does not have the log base form, if you can't hit the math button and scroll down and find log base and be able to type the formula in directly into your calculator, you can use what we call the change of base formula. Okay. Now, with the change of base formula here, what it essentially allows for is when you can't type in say the log base a of x here, what you could do instead is you could change the base to the plain base of log here and rewrite it as the log of x over the log of a. These will compute to the exact same thing. And actually, you could convert it to natural logarithms as well. The log base a of x is the same thing as the natural log of x over the natural log of a. Okay. So, if we wanted to evaluate the log base 8 of 124, you could do that on your calculator if you have the log base function on your calculator. And like I said, all the newer calculators have it. Most of the calculators that aren't like over 10 years old have it. But there still are some older calculators floating around out there that don't have it. If you're unable to type it in just like this in your calculator, what you could instead do is type the log of 124 over the log of 8, and it will give you the exact same answer you would get as if you typed this in your calculator. Okay, that's the secret to the log base formula. The other cool thing about this is it holds for graphical options as well. So if your calculator like I said, if you have an older calculator that will not type in log base 3 of x, you could instead type it in as the log of x over the log of 3, the log of 3 over the log of x, or the log of x over the log of 3, and it will give you the exact same graph as if you typed it in this way, the original way. It will also give you the exact same graph if you decide to type it in as the natural log of x over the natural log of 3. Okay, these are all the same graphs. Okay, just different ways to write them. Okay, let's do one more example before we call it a day. It says if $10,000 is invested for T years at 10% compounded annually, the future value is given by S equals 10,000 times 1.10 raised to the T. In how many years will the investment grow to $45,950? Okay, now essentially all we're going to do here is substitute in 45,950 for our S. Okay, then we just are essentially walking it down and solving. The first step would be to divide by 10,000 on both sides. Okay, this will leave you a 4.5950 equals 1.10 raised to the T. Then you're going to want to convert that to logarithmic form. So it'll be that T equals log base 1.10 of 4.5950. Your calculator can express this if you have the log base function. If not, you can rewrite it as the log of 4.5950 over the log of 1.10. And if you get that, you should get approximately 16. Now, it doesn't turn out to be exactly 16, but it's approximately 16. I believe it's 16.0001 something something. Now, this tells us that this investment that we made, this $10,000 investment we made compounded at 10% annually, will grow to $45,950 in 16 years. That completes Chapter 5.3. Please log on, try to do your homework. If you have any questions, reach out to me. Y'all have a good one.